Hello, friends.
Hola, Juan. ¿Cómo estás?
Bien,
Hello.
Hola. Hola, nene.
Hola.
Si hay preguntas, podemos hablar sobre estos.
Yes. About the last class, about jets, was how is possible to accelerate those particles? It means what kind of mechanisms can do that? How can energy be transferred from, I don't know, a black hole or neutron star, right, into an astrophysical jet? How can energy be transferred?
What are the ways to do that? What forces are available?
Yes, because it's the most energetic phenomena in the nature, right?
Yeah. How do we do it on Earth?
Excuse me?
How do we do high energy accelerators on Earth?
Yes, how?
Yeah, I'm asking.
magic.
Maybe
Not magic. It's not magic.
maybe rotation, black hole in a very fast rotation, or neutron star in fast rotation.
But on Earth, how do we do it? We don't have a black hole.
Yes.
We don't have a neutron star.
Fields. Electromagnetic.
So we have giant particle accelerators. But what do they look like? Right, there are these giant tubes that go around in a circle. Why do they go around in a circle? Because you're and what are they doing? Right, you're each part of that is pumping energy into the particle so that it'll go around. And so it has some sort of orbit, and you are accelerating it. And what are the things you can accelerate? It's either got to be an electrostatic force or it's got to be a magnetic force, right? You either have to do the electron velocity times the magnetic field curl, and that generates a force, right? So you're basically accelerating with the magnetic field. Or you have a pulse you're injecting with a Coulomb pulse somehow. I mean, those are the only two ways you can get you can drive or accelerate a charge, right? And so those processes now take them and put them on your neutron star or put them on your black hole. And where are you getting that from? So you have in the neutron star, you have a solid body with a magnetic field that's rotating maybe a millisecond. Something the mass of the sun is rotating every millisecond. And so it's just creating this magnetic field, which is being able to accelerate these things, these electrons, right? Or you have a black hole with a disk, and the disk is rotating around, and you're getting the magnetic fields are coupling, right? And they're bunching up, and again driving something as a jet or as a wind. But that's how you get them accelerated. Now the big trick is how the hell do you keep that magnetic field in that sort of shape a whole megaparsec or 100 kiloparsecs? That is the $1 million question. Right? That's the Nobel Prize question.
One last question. Hawking radiation has been proven? Hawking radiation.
Hawking radiation. Yeah, well, we're not really, I think I'm not going to talk about that directly here, mostly because it hasn't been observed yet. But I mean, the whole point of Hawking radiation is just it, and it actually comes down to something close to what we're going to be talking about today. So I didn't put it as one of the observational things, but I could have. So maybe it's better to talk about it at the end, if we have time, or next class, where you can see it a little bit better. Okay. Any other questions about past lectures? No. Okay. So today we're actually going to talk about something that isn't in the book, for better or worse, and so that's going to be pair production and annihilation. And so I assume you guys had some elementary physics, and I assume you went over this process, at least in some amount of detail. And so what do you need for pair production? If you want to produce a pair, what are you producing, and what do you need to produce it? And a pair of what?
It's when you produce a particle and an antiparticle?
Yeah.
By production.
Exactly. Yes. So you have the particle and the antiparticle. Typically, it's an electron and a positron because those have less energy, but you could have a proton and an antiproton. A neutron and an anti-neutron doesn't really make as much sense. Yeah. So the main one we will be talking about is the proton and the electron and the positron. And so what do you need to create those two things?
High energy photons, very energetic photons.
How much?
Relativistic ones.
Photons are relativistic by nature, but right, I mean they're photons. But what in terms of energy, how much energy do you need typically?
Very high frequency.
Sure, I want a specific answer.
At least the rest energy of the electrons.
Exactly, you need the rest energy of the electrons, right? So you need each positron and electron have a rest energy of 0.511 MeV. So you need at least 1 MeV of energy from some photons to generate that. We'll come back later and actually talk in very specifics about that, because actually you don't necessarily need that, or you need something slightly different from that. But roughly speaking, that's great. On the other side, if you have a positron and an electron, you move them close together, they will annihilate and create photons, right? And they will create photons with at least an energy sum that is greater than 1 MeV, more or less. But they could have more because the particles could have some momentum coming in, right? And so when they annihilate, that extra momentum is going to go somewhere. It's going to go into the energy of the photons as well. Right. So this is what we're talking about, this process. And there, of course, we can frame it in a better way, right? We can say there's a cross section for this process to happen. So if you take a positron and an electron, how many of them do you need in some small space in order for you to get an annihilation, right? And so we can then talk about, as a function of the density of particles, what is the cross section for an annihilation? And vice versa, we can say, okay, we have a density of photons, and what is the probability that two of them will collide and lead to an annihilation, or sorry, not a pair production. And so we can devise a cross section for that. So that's basically what we're going to be talking about for the rest of the class. Okay, so let me find wherever the hell I am. Here we go. All right, so we can step back a little bit, and one of the sort of realizations of why this could be an important process, or an important limiting process, that whether photons create pairs or whether pairs create photons, was around the study of black holes. And so if you have energetic particles and you have photons, there's always the possibility that if the density is high enough, you might have collisions between them. And so the photon-photon collision would produce the photons would disappear and produce electron-positron pair, or vice versa. And so it was sort of initially a theoretical argument that this could be an important absorption process that could be a limiting process in the high energy universe. And this is sort of realized when people started thinking about black holes. And as you get towards a black hole, obviously if we can measure a temperature of the protons really close to the black hole, a few Schwarzschild radii away, the velocity or the virial temperature of those photons then becomes very, very large. And so we can just estimate that. So the kinetic energy of a proton that's orbiting at 3 Schwarzschild radii from a black hole will be of the order of this, which will be of the order of this. And so this is a large number. Right? This is 150 MeV is a huge amount of energy compared to the energies we were just talking about. And so obviously the protons that have that energy can interact with electrons and can potentially, through Coulomb interaction, can drive them, accelerate them to a similar energy level. And of course, if you have electrons which are moving around at 100 MeV, they're going to emit radiation. And so you have a very compact region around a black hole, which was going to have very energetic particles and a lot of photons, right? Which is the thing we need to kind of make this process potentially viable. So that was the sort of thinking. And of course, the protons would be able to cool faster, and they will cool by accelerating the electrons. And so you can kind of continually inject this energy as protons are kind of moving closer in, right? So they lose some potential energy, make it to kinetic energy, and then they cool by accelerating electrons, and then the electrons radiate. And this process kind of sort of continues. The other kind of interesting timescale here is, or interesting ingredient rather, is that AGMs vary quite rapidly. And by causality arguments, a coherent variation from them, should vary on sizes which cannot be sort of larger than the light crossing time. And so, these things will vary, and that region must be very small. And the amount of luminosity that they vary by is quite large. And so, there's interesting effects there. So we have very dense sort of numbers of photons. We have very energetic particles. And so we have a possibility of having collisions between particles, collisions between particles and photons, and collisions between photons, right? And as people started launching gamma ray observatories, they realized that AGN were, in some cases, a source of gamma rays, so a very efficient source of gamma rays, so blazars or GRBs as well, so dying stars that have sort of jets tunneling out of them. And so, with this sort of energy production, people realized that there should also be the potential for pair production there. And so it turns out that there are other processes which end up dominating over pair production. So it generally is a limit that never is reached, but it still provides useful physical limits because we see the energy coming out in different ways. We can kind of estimate that the conditions are not right for pair production. And so we can use that as an upper limit on some particular physical situations. So that's just some background here. Okay, so we're going to look at this in two different frameworks. And one is going to be for a thermal plasma, and the other is for a non-thermal plasma, right? So a sort of thermal distribution of electrons and a power law distribution of electrons. And then there's two sort of fundamental results of the pair production for thermal plasmas. And we'll sort of look at this in more detail. And then we'll also look at how this sort of behaves when the particles are relativistic, but in a non-Maxwellian distribution, so the non-thermal distribution. So let's first consider the Maxwellian distribution. So we have a temperature of the system. So the electrons are with a temperature T. And we then have some photon field as well. And so we want to look at the production of the positron and electrons. And so we can redefine everything in terms of the rest mass of the electron, right? So the temperature of the system can be defined as a ratio of the rest mass, which is capital theta here. And then the energy of the photon can be redefined as a function of rest mass as x. And we can then think about the ingredients that we need, right? So we need some number density of positrons and electrons. We need some number density of photons. And then we have, based on these, we have some production of new pairs of positrons and electrons, and we have some annihilation of pairs or production of photons, right? And obviously we need certain densities of photons to create the pairs. We need certain densities of pairs to create the annihilations, right? Finally, these, we have these ingredients. There's one extra one, which is the escape rate of the leptons, or the photons for that matter. But this escape rate is important because it's sort of an outlet if things are diffusing out and they're not being retained to be available for the rate of annihilations, for instance. Okay, so with that, we can then start to think about what are the rates at which we can go from one to the other. What are the different channels for that? And so we can produce the positron-electron pairs in a variety of different ways. The most obvious is the one we just talked about. All right, two photons meet in some area of space and they produce a pair. And we can associate a rate at which this happens. So this is the rate at which this happens. And that's going to be related to the electron radius, the speed of light, and the density of photons squared, right? So we need the density of one and the density of the other, so we have density squared. And then this F factor here is a dimensionless sort of average, which is it's a cross section based on the Maxwellian distribution. But for a different distribution, we would have a different cross section. So that's the most obvious channel, but there are other channels. So one is a photon interacting with a proton. And so a photon interacting with an energetic proton can actually also lead to a pair, and then the proton comes in. So you steal some energy from the proton to create this. And there's a rate associated with this, right? Which is, again, related to the electron radius, the speed of light, the number density of photons, the number density of protons, the cross section, and this extra factor here, which is, if it's just the fine structure constant, but generally every time we have a particle, we will introduce the fine structure content as a factor here. And so likewise, you could do the same process with an electron. And so here you have the number density of electrons instead of protons, but otherwise is identical. And then what's interesting is you can actually have an interaction of two very fast electrons, and they could actually lead to a pair production, and then slower electrons could come out. And so here what you want is the number density of positrons, the number density of electrons squared, because you need them. And you have two factors of the fine structure constant here. And then you have some cross section. Likewise, you could do this with electron protons. In theory, you could also do this with proton protons. But in general, the cross section here ends up being very, very small. So those are the processes that create the pairs. And we have the processes which take them away, like the annihilation of pairs. And so the annihilation is simply this, and that will lead to the photons. And so typically there are not really interactions of three bodies that will meet and then annihilate. And so this is the dominant one here, but you also will have escape here as well. So what do you need here? You need the number density of protons, positrons, electrons. This is the cross-section for annihilation. And again, you have these sort of constants here. And likewise, you have a rate for escape. And everything is framed in this factor of R squared C, which is kind of related to this cross-section. Okay, so that's, and we can think about the factors here of the fine structure constant. Generally, you can think of it as alpha to the A power. And A equals 0 is for photon-photon interactions, A equals 1 is for particle-photon, and A equals 2 is for particle-particle. Right? And that kind of frames everything pretty decently. So hopefully this makes sense. It actually, in this case, actually interesting enough, you need the number of density of protons plus the electrons plus the positrons, whereas here you have this squared. Okay, so we have to do a detailed balance between all of these, or make some assumptions about which one's dominant and do a detailed balance there. And of course, these are potentially functions of the energetics of the system, and they're functions of potentially the photon field as well. So if we were dealing with a Maxwellian distribution, and we have particles here, even if the global temperature of the system is lower than a few MeV, you have the tail of the distribution. So you'll have a tiny fraction of sources which could potentially be available for this process, right? So even if this thing is much less than 1, you still might have a tiny number of sources which could go through this pair production. Okay. So a little bit more about the F factors, these cross sections. So in the regime where you have a Maxwellian distribution and it's very, very small, the temperature is much less than the sort of normalized rest mass. Your F factors are sort of, these don't really matter. and your F factors are dominated by these three components here. If this is much greater than 1, then they have slightly different sort of Taylor expansions, and these factors actually tend to be more, they tend to be somewhat relevant now. There's two versions of these. One is for a Wien component, and then one is for a power law component, just to sort of put them in perspective. And so these F factors are the, as I said, the main rates at which the pair production mechanism is occurring or the annihilation is occurring. And here, these are only showing the photon-photon or the particle-particle processes. There are F factors for the photon particle as well. And so typically when dealing with this, you need to know the spectrum. And so this is why we put this here, because the spectrum actually has some influence on the F factors as well. And so you can kind of glean something about this. If you think about the distribution of electrons in a thermal distribution, it might have some distribution which looks like this, whereas it might have a distribution which looks like this for a power law. And so you can kind of see in this form, you have a sort of expansion of this, whereas in this form you have an expansion which is related to this. Okay. So going through and deriving this is not necessarily trivial, but you have a lookup table. You can go and at least sort of find what these are. And then of course the escape fraction is dependent on the velocity of the pairs, right? So we just frame it in terms of v divided by c, so it's p escape. So if we want to think about a situation which is what we call stationary, or something which is in equilibrium, then we're talking about the rate at which pairs are made is equal to the rate at which they're annihilated, right? Seems pretty simple. And so all we would do is say, okay, let's plug in what we have for these rates, right? Which are all of these things. So all of these are the sources, and then this would be the annihilation. At the moment, if we're assuming that the system is closed, we don't have to care about the escape. But in reality, some particles will escape. So we might want to put an escape component here as well. But just in simple terms, we just want a balance here, right? And so we can solve this equation by plugging in adding all these things up and plugging in the various F terms. And what we can kind of notice here is that for the particle-particle pair production processes, the F terms end up being increasing functions of the temperature for the most part. And the pair annihilation rate is a decreasing function of temperature. So if we go back here, right, this is temperature. So this is slowly increasing. And then we have a 1 over temperature component here squared. And so this is sort of falling off. This actually is increasing with alpha. This is again sort of increasing. This is sort of increasing flatly. The annihilation is actually similar to the production at very high energies. At low energies, you have this exponential fall off and this exponential fall off, and then you have something which is flat here. And so the F terms here, generally speaking, if you look, so Fa is the annihilation term, it's roughly flat, and then it has a decreasing term here, right? So it's flat, and then it goes like that, whereas the electron EE1 is actually increasing slowly with temperature, right? Although this is to the third power, so it's a decent function. And so this thing is increasing as a function of temperature. And what's sort of interesting here is that obviously you have a regime where annihilations dominate, and you have a regime where production dominates. And so you have a sort of temperature at which afterwards you will start overproducing pairs. So for a given temperature, and this is obviously a temperature which is much higher than the rest mass or the rest energy of the electrons, you will start to go into a non-steady state solution. And so a steady state solution is going to be one where you're sitting in this regime. So basically, if the temperature is high enough, the possibility of producing more pairs will be higher than the ones that are destroyed, right? And so we're in non-steady state. So in order to be in a steady state, we require this condition. So this thing equals 24, or the max temperature has to be greater than 12 MeV. And so assuming we were in that situation, we can kind of consider a plasma which is pair dominated. And we can neglect here the original electrons associated with protons, and we can just set the number of electrons equal to this here, right? So if we're in a situation where we've created the pairs, and those are the things that dominate, so we have equal numbers of these things, then we can neglect all the particle photon processes, which tend to be lower for the most part anyway, and we can think about how do we achieve this. And so we can plug in our two components here, which are basically speaking, are pair production via the two photons, and then the pair production via the two electrons. And so these are going to be the two dominant ones, and then we have our annihilation process here. And for this to be in steady state, right, this has to be an equality, and so we can put these in terms of a ratio of the number of photons to the number of electrons, and that's going to give us this ratio of these sort of F factors, or the cross sections. And in general, this has to be greater than 0 for this thing to hold. And what that means is that 2FA has to be greater than this, right? And that kind of comes back to this thing here. So this thing has to be greater than that thing. So it has to be in sort of this regime. Otherwise, we go into a non-steady state solution. And we get this sort of runaway effect. This actually will lead to, if it's a combined area, this will lead to the overproduction of pairs, and eventually you'll have some sort of exodus of these pairs, which will lead to some sort of explosion. Okay, is everything clear so far? Are there any questions?
Yo tengo una pregunta.
Yeah.
En el proceso de aniquilación, ¿se genera solo un fotón o pueden ser varios?
Dos.
Ah, 2 fotones. Ok.
Sí. Necesitamos una conservación de energía y momento.
Ah, ya, perfecto. Bien.
Sí.
Gracias.
Okay. Others? In fact, this is why we go back here. Yeah, this is this production mechanism here, right? So this will equal 2 photons. Yes. Okay. Okay. So aside from this, which I think is not super straightforward, the rest of it is kind of just simple energy balance sort of mentality. So we have this, and again, yeah, we sort of had this picture here, and usually what happens in this case is that we'll have an increase in the energy of the system, and that increase in energy will increase the temperature. As the temperature approaches the rest energy of the electrons, pair production will start to occur, right? Because we'll have enough energy available to start producing pairs. And when this happens, new particles are created. And so the energy per particle should then be distributed over more particles, and the KT will then decrease. And so this is kind of a natural mechanism for cooling once a system gets to a temperature close to this. If these things are sort of confined, then you can, say confined by gravity or confined by some pressure, then you can start to have interesting effects. We can talk about, there's something called a Wien plasma, which is a plasma where the photons and the particles are in equilibrium via a scattering process. So there's no absorption and re-radiation here. It's just the exchange of energy via scattering, or Compton scattering. And so for this Wien plasma to effectively take place, obviously the cross-section, the optical depth for the scattering process needs to be greater than 1. And so what this means is that the number of electrons and times the size of the region times the Thomson cross-section needs to be greater than 1. And in this case, the spectrum here is not going to be a black body, right? Because we don't have reabsorption or reemission, it's just scattering. And so we can imagine that under these conditions, if we have some photon production process, maybe this is brimstone because it's hot plasma, and so we have electrons, naturally we should have some production of brimstone, then the spectrum will look like this. The number density of photons, the increase in photons will be proportional to this. So the top end of the brimstone spectrum. And we can rewrite this not as energy, but as X. And so it looks like this in terms of X, right? And so conveniently we have an exponent, which is relating our photon energy to our electron temperature, right? Our two key parameters. So this is the photon production rate. And we can then think about the density of photons as being this quantity, right? So this is the total density, this is the production of them. And so this total density is going to be equal to the production of them times the size of the region, the light crossing time, effectively, and this potential for scattering, right? So this cross section here, or the optical depth for this Thomson scattering. And so if this thing is much less than 1, then the difference between this and this is simply the light crossing time inside the source. And so you will create a photon, say, in the center, and you need some time for it to escape. That's all. And that'll be the difference between the total number and the increase. Is just you have a number here, and if you wait for light crossing time, you will have another photon kind of that comes across. If tau is much higher than 1, then what happens is that you get a production of a photon over a small chunk of the total size, right? And so then, generally speaking, the transit time to go across the region is going to be lengthened by this sort of random walk process of scatter, 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 scatter. And so you will end up doing tau squared scatters as opposed to tau scatters. And so the distance traveled here will then be proportional to this, and the time needed to escape will be of this order here. And so we have tau on each side here, we can cross out. So the total time will be equal to that. And so now we can think about the total luminosity of photons coming out of this system. Right, so that's the production of photons, and that's going to be the volume, and then the rate at which they're produced, and then the energy of each photon being produced, right? And so we can plug in here our value for this thing, and so we have this thing is proportional to the total number of photons divided by 1 plus tau, and then some factors which were here. Right. And now we just want to do this integral, which isn't too bad. So if tau is much greater than 1, then this thing just turns into tau. If tau is much less than 1, this thing is just 1. And we can also note that tau here is proportional to the cross-section, the size, and the number density of electrons. And so typically what this means is in a high tau situation, you have something which is, you're taking the integral of something which is the number density of photons divided by the number density of electrons, right? So the luminosity depends on the ratio of the photons to the electrons. And so if we have a pair plasma, when the pairs start to outnumber the original electrons, then what happens is these numbers are just fixed by the F terms. And so the luminosity coming out of here then plateaus at some value, which is fixed by these F ratios that we calculated. Then another thing, if we have a Wien spectrum, the average energy here is going to be 3 kT. And so we will know this more or less. And so when we have very, very large luminosities, what happens is the pair production process that typically dominates is the photon-photon. For this ratio, right, if we have this ratio and it's fixed by this ratio here, and if we assume we're in the low temperature regime, then what happens is this ratio is equal to this, it's equal to this thing, just plugging in our values here, right, for this thing, and for, I guess, let's see, this, is that right? It's the number of photons, the number of, oh, it's the annihilation, and yeah, sorry. So this is FA, which is just pi, and then this thing, which is this thing. So we have pi squared here. And so this is going to be equal to this. So this is we're going to take the integral of this thing, right, which is this. And so it's the energy times this. And this is the temperature. And so as the temperature increases, the luminosity will increase to some point, but you have this extra factor here of 1 over the temperature. And so this complicates things a bit. And so as the temperature is very, very small, this is fine. As this thing increases, this kind of kills it. So you have something which is increasing, something which is decreasing. And so we had to plot it to see what's sort of going on here. So if we sum all this together and do this integral, we have something which looks like this. And so we've just, so we have this component here, and we also have a sort of energy here. And so we end up with this component still, and we have an extra energy term in here. And so this thing ends up being proportional to this value. So that's the luminosity that comes out. This thing is dependent on the size, right, and the temperature of the system. And we can redefine the luminosity in terms of something that is called the compactness. So the compactness is the luminosity divided by the size of the region and some extra constants here. And so what's sort of interesting about this is that if we have a fixed R, then what happens is the low luminosity, basically high luminosities only come out for low temperatures because this term dominates at high temperatures. And so in terms of the compactness, we have, if we plug this thing back in, we have a compactness which looks like this, right? So it has the same functional form, but we've gotten rid of all these constants here and just have a factor. Again, this is only when the electron temperatures are much below the rest energy. So we're just looking at the exponential tail of this distribution. And so if we plot the compactness as a function of temperature, it ends up looking like this. And so we have a minimum around the rest energy of 1. And then we have up here, this is the maximum at which above that you go and you go into a non-steady state. And then if you go below it, you have at very low temperatures, you have a high compactness. And that either means if you have for a fixed R, that means that the luminosity goes up, right? Which is what we were saying here. So the combination of this thing mostly wins out here. It also increases as you go up in this direction, but very slowly. And at some point, you no longer are in a steady state anymore anyway. So this is all a little bit, it takes a little bit of time to wrap your head around this. But the point here is that we have a sort of minimum that comes around here. So we have for temperature equals 1, the compactness is at a minimum. And so for a fixed region, that means the luminosity is at a minimum when we're around here. For a fixed luminosity, what that means is that the region the compactness will go down. So that means that the size for a fixed luminosity will be increasing, if that makes any sense. But basically to have a large compactness, you can only really do that when you have relatively low temperatures. Okay, so that's one regime where we can talk about this pair production. Now, the other possibility is that we don't have a thermal distribution. And likewise, what we could think about here. So we made this approximation, right, under the assumption that this held. And so we had this approximation, which goes like that. And so actually what I neglected to say is obviously if we go above this, right, if KT is much higher than this, then we need to make different, we don't use these two terms, we use these two terms. And these two terms are actually pretty close to being equal, right? So they cancel out. And so in that case, what we end up having, this is more or less fixed at 1. And so all we have is an integral of energy. And so then we have something which increases somewhat linearly with the energy, right? Which is why we see this increased thickness. And then obviously we have a hard time doing an expansion of this thing right around here. So we have a kind of connection here where this isn't exactly valid, but there's some sort of connectivity here between these two asymptotes. Okay, sorry about that. I've completely spaced on that divide here. Okay, so then that's the transition between the two regimes of different temperature components. Okay, for the other case, we could have a non-thermal distribution of electrons, and typically we can approximate that by a power law. And so let's say that we have a non-thermal distribution of electrons. We have a non-thermal plasma. The densities of non-thermal plasmas are typically pretty small. However, the particle energies can be very, very large. And so they can be well above the rest energy of the electron, right? And so even though the densities are small, the energies are large, and so the production rate can actually still remain relatively large. And so you can still produce a relatively high density of energetic photons, even though the plasma is rarefied. So the main mechanism here ends up also being photon-photon pair production. And if we think about energy conservation of energy conservation and momentum conservation, basically we can show that the energy threshold where pair production begins is set by this inequality here. And here, this factor of theta is relating the photons coming in and trying to collide. to produce a pair. And so theta equals pi is a head-on collision. And so theta equal pi, right, this will equal -1, -1, -1 is 2. And so this is going to be 1. A value of theta equals 0 means a tail-on encounter, which can't happen. You can't have photons encountering if they're going in the opposite directions, right? And so even though this obviously would be 1, 1 minus 1 is infinity, so you would have this thing is greater than 0, but you just can't have this process happen if that's the case. Now, this is a little bit strange. So this multiplicative of the two photons has to be greater than 1. And that's a little bit different than what we had thought about at the start of class, which was that we needed the total energy to, for energy conservation. We wanted that the two photon energies had to equate to the rest energies of the positron and the electron, right? And the reason this isn't the case is because the encounter between the two photons needs to be in the frame of one of them or the other. And so the photon interacting with another photon is, we have to transform the frames. And of course, then we have a Doppler effect or a Lorentz factor that comes into play in the transformation. And so we can actually have a photon which is say higher than the normalized rest energy, and a photon which is much less than that. And the two of them can combine to create this, which is kind of a little bit interesting to think about. And so the threshold condition basically needs to be calculated in the reference frame where the energies of the two photons are equal. And so to sort of illustrate this point, let's examine this head-on collision. And we don't have equal energy photons. And so we have in the frame where the energies are equal, how do we go from this frame to this frame? And we need a transformation of the Lorentz factor, gamma, to do this, right? So we want to go from the two photons here to a frame where they're equal. And sort of what do we need here? So in this frame, basically the angle will still be head-on collision. But the energies here will be transformed like this and like this. And so this, obviously the multiplicative of these gets rid of the gamma, but it allows you to have a photon which is much less than the energy and much more combined to give you the right sort of energy product you need to make the pair production. And so in the frame where we're going to add the energies, this has to hold, right? So this is the original sort of equality here, or inequality. So we have to have at least this much energy to make the two leptons. And we should have that this is roughly equal. And so what does this mean? This means that this quantity here, this ratio, has to be equal to this. And that means that this thing plus this thing, right, if we transform each of these back, this combination has to be equal to or greater than this. And so we can rewrite this thing, moving things around, and it turns out that equals this inequality here. And so what does this really mean? And so actually, I want to go here, but basically what this means is that we have some energy of photons. We have a photon with an energy x, and we have one with 1 over x, and the combination of those two will give you a pair production. Even though this one has enough energy well above the rest energy of the electron, and this one has energy much below it. And so what this sort of means is that, let's say we have an energetic photon with an energy of 4 times 10 to the 14 eV. So it has a huge energy above the rest energy of the electron. It can interact with a photon with an energy of this, which is the typical energy of the microwave background, and produce a pair. likewise, we could have a 10 to the, I think this is 10 to the 12, no, 10 to the 11 EV, and that will interact with a 2 EV photon, aka starlight, and you would produce a pair. And then likewise, you could have maybe a more typical situation. So something with an energy of a few times 10 to the 8 EV, and that would interact with X-ray photon of 1 keV and produce a pair. Right, so you can see that there's this balance between the two. But what's interesting is that the most energetic photons can reach from a pool of photons which are actually superabundant. Right, the microwave background is ubiquitous; it's everywhere. And so the possibility of this happening for very high energy photons is very, very high, because just the number density of these photons. And if you say that this photon is traveling over a large distance, then at some point the cross section will be enough so the tau will be 1, and you will have you'll produce a pair, and you'll take that photon out of existence. And likewise for this combination or this combination. But these are very common. These are less common, but they're still pretty common. These are relatively uncommon, but still you could have that happen. And so if we think about the cross-section, this cross-section actually mirrors in many ways the Klein-Nishini cross-section. And so the cross-section has a peak, not at this multiplicative of 1, but about 2 times, a factor of 2 times that. And so if you look at the cross-section of the photon-photon divided by the Thomson cross-section, you see that it rises up to a peak at 2 and then has a decay like this. And so you can, obviously the benefit here is that you will have the cross-section will seek out a photon which is inversely proportional to it with respect to the energy, the normalized energy of the electron. So you have, so the cross-section is 0 below the threshold, and it decreases above this peak, and you have a gamma ray photon here with an energy X. It can interact with any photon which has X greater than 1 over X. But it's preferentially going to interact with a photon which is close to 1 over X. And we can consider this the target photon population. So this is what this was trying to convey, was just that if you have a photon that's like this, it's actually going to look for photons that are around the microwave background energy. And this energy photon is going to preferentially look for photons that are around the starlight energy and interact with those to produce a pair. Right? The cross-section is going to be highest for these particular photons. Okay, so let's see. Well, I should ask, are there any questions so far? No, okay. Speak up if you have any questions. So we can think about the optical depth of this process of a photon and a photon meeting somewhere and having the right energies to produce a pair for a given luminosity of source. And so we can assume that the luminosity of these photons is at high energies. We need obviously a photon that has at least an energy of this, and photons of this energy are going to typically interact with photons of the same energy, right? Because they're close to the rest energy of the electron. Whereas, say, a photon of 5 MeV has X equals 10, and so it's going to typically seek out a target photon 1 over 10 or 50 keV, and vice versa. So we can think about in a similar way to the optical depth, this thing depends on the cross-section. And so it also depends on the density of targets, of target photons, the number density of photons, and the size over which this process can occur, right? The path length over which it can occur. And so if we think about the number density of 1 MeV photons, this is the energy density times 1 eV divided by 1 eV. this thing is equal to the luminosity, the X-ray luminosity, divided by the volume. And we can think about the volume in terms of the surface area and the light crossing time. And so this thing we can relate to this, right? And so we know that tau is equal to, if we go back here, this cross section is equal to the Thomson cross section divided by 5. And so this thing is going to be equal to the cross section of gamma gamma, or this thing, times the radius, times the number density of photons, right, which is just this. And so plugging all this in, we have something which looks like this. And now recall the compactness parameter that we had mentioned before. So this thing, basically apart from a numerical factor, depends on this compactness. The compactness is given by this. And so the cross section is just the compactness divided by 60 at 1 MeV. And if we can also measure this in terms of Eddington units and Schwarzschild radii. And so the compactness here could be this luminosity as a function of the Eddington luminosity and this radius as a function of the Schwarzschild radius. And we could think about the maximum that you could possibly get, right? How compact could you make a source? And that would be something where you had the Eddington luminosity and a Schwarzschild radius, more or less, and then you're just dependent on the ratio of the proton to the electron, which is roughly 2,000. This is roughly a factor of a few, and so the Eddington limited compactness would be about 10 to the 4. Right. And so this would give you a tau of something like 500 or so. Okay, so if we now think about a spectrum of photons, and the spectrum has a typical power law shape. So it has, the flux at some wavelength goes as frequency goes as the frequency to the minus alpha, and alpha is a spectral index. So it goes like this. So we can think about the spectrum is going to extend above this limit. And so we have photons that are available, giving enough energy to enable the pair production process. And we can calculate an optical depth for this to happen. And so we'll consider a photon here with this property. And so we need to know the number density of for each photon that's up here, we need to know how many photons are available around this peak target frequency or energy to do this, basically to produce this pair. And so, that will give us a limitation right there. And then we also want to know that, we know that the cross section is going to decrease with increasing energy of the targets. And so the increasing energy of the targets means the cross section decreases, and then it also stops right here. So we have some sort of functional form which is dependent on this. We also know that if in general we never have anything where it's very rare that we have sources which have a spectral index where we have a larger number of photons here than target number of photons. It does happen sometimes, and gamma ray bursts, for instance, can have a flat spectrum that might be conducive to this. But in general, you have fewer here than here. So it's really limited by the number here. Actually, sorry, it's really not limited by the number here. It's limited by this number here, and you generally have enough photons here to make that happen. If it was inverted, right, then you would have too many photons here and not enough photons here. And then you would be restricted very predominantly by the number density of photons here. At any rate, we have some photons here. They're going to interact with photons with this target range of energy to produce a pair. And we know that the cross-section decreases with increasing energy. And we have a power law where alpha is greater than 0. And so we can approximate the number density, the number of target photons, as just being 1 over x times the number of 1 over x photons. This is going to be the number of target photons here will kind of be related to this. We can see this sort of symmetry here. So we have, if we think about the flux is going to be, here. So it's going to be, in this case, it will be at this energy. We'll put 1 over x here. And then what do we have? We have, actually, I think I have it in the next slide, which it's maybe slightly clearer. But the flux is the number of photons times the energy. And so we want to divide the flux times x. And so we have fx divided by x is giving us the number at any point here. And then we also have some sort of factor which depends on the flux is dependent on this ratio here. All right, so I actually have it here. So we have this tau value, and so that's equal to our cross section r, and then the integral of the number, and we want anything between this value and this. But we can make a simplification that it's going to be dominated by this. Right, so if we just evaluate this at this value, we're going to get pretty close. So we do that, and so we plug in here what this will be. So this is n at this, and then this will be, we have an extra value of x here, and so we roughly approximate it as 1 over x. And we this thing is going to be this right here is proportional to this divided by this. And then we have the 1 over x here. And so this thing is proportional to x minus alpha. This thing will then be x minus alpha minus 1, and then times this will be basically 1 over x to the, well, it ends up being 1 over minus, or x, 1 over x to the minus alpha, which is x to the alpha. And so this tau process here is proportional to the input photon spectrum, but in the opposite sense. So we don't have the minus alpha here, we have an alpha. So this thing increases with increasing x, right? And so there are more target, basically what it's saying is that there are more target photons because of this inequality. So we have some spectral index, and we have a spectral index of the number of targets. And we can do the same calculation. We could do this for a broken power law. We could do this for other things as well. And so it generally should hold as long as we have something which looks like this, not something which looks like that. So it's not, as long as you can approximate this. So we can then think about a radio transfer equation, which is factoring this in, right? So we figured out what tau should be, or how it should be proportional. And so we know the absorption that goes in here. And so we can think about the radio transfer through a slab, which is a little bit simpler to do than a sphere. And so we have the intensity of the photons as they move through this slab, which has some density of photons in it, as the emissivity of those photons and the absorption constant, or the absorption coefficient. So it's the ratio of this times this quantity here, 1 minus the exponential to this optical depth. And we just add this factor of r here and here, but we wouldn't necessarily need to, right? This is just equal to 1. And so this is the intensity at this particular value of frequency. And this is the emissivity at this frequency, the absorption coefficient at this frequency. And we can note that this quantity here, right, this is the reason we multiply by r, is equal to this. And so we can rewrite this as just 1 minus the exponential to minus tau over tau. And so in the extremes, either tau is very, very smaller than 1 or is much, much greater than 1, we have the following expansions. And so for low tau, this is just proportional to the emissivity times the volume, the path length that we're going through. And so this is just proportional to the original spectrum that we had. If tau is much greater than 1, right, then we have our emissivity, but we have it divided by tau. And so we end up having something which comes out as x to the minus 2 alpha. And so what that means is that if you have a high absorption for this process, you originally had alpha coming in, right, a spectrum like this, and now coming out, you break it down. So you've lost some of the high energy photons, and there's a break in the spectrum, which is produced by this process, which is kind of interesting. So what it basically looks like is you have the input here, or you have the original spectrum, which isn't really modified because there's tons of photons, and you don't need to take very many away for this process to happen. But on this side, you have these photons are being depleted and are creating pairs. And you'll have a break, which happens roughly at this energy of photons, which is a little bit above by about a factor of 3 from the rest energy of the electrons, the normalized rest energy frequency. And so this is where you would have tau equals 1, you'd have this break. That's all great. However, we've just produced some pairs, and those pairs will emit radiation, which can then modify the spectrum, right? Because they may have some energy going with them. So there may be a magnetic field, there may be protons, whatever. There then is also the possibility that the pairs could annihilate and create a new set of photons too. And so generally speaking, each of these pairs is going to share the energy the photons created. And so typically they're going to have an energy which is proportional to this, and the radiation they produce is going to be at energy smaller than x. Now, if the energies end up being high enough, you could generate secondary photons, which would then modify this spectrum somehow. These secondary photons would then be available as targets for this process again, et cetera, et cetera, et cetera, et cetera. And so you can have a highly nonlinear process depending on exactly what the photon field is and so forth. So it's not necessarily trivial to calculate this out, but this is roughly what is going to happen. One of the observational impacts of this is actually pretty interesting and cool, and is that one of the issues here is obviously tau is proportional to R. And so if you have a source and say you have a uniform photon field like the CMB, which is is all over the place, and there's a density of cosmic ray photons, or CMB photons everywhere. And as you go back in redshift, the density increases, right? And the temperature of the CMB increases, which means you have more photons available. And they are closer potentially to lower energy gamma rays. So as a function of redshift, you have an opacity for high energy processes. So things that emit gamma rays at redshift 0, we can see. As you move that same source out to farther and farther distances, there's a possibility that as the photon is trying to get to us, it encounters another photon and creates a pair. And we lose that photon, we don't see it, right? So there's an opacity of the universe towards gamma ray sources at high redshift. And this is what's being shown here. So this is the attenuation as a function of percent versus the energy of the photon. And this is for different ages of the universe. And so you can see that for a relatively high age, the attenuation is 100% all the way up to sort of 200 or 100 GeV. And so for sources that are emitting at, say 2 billion years after the Big Bang, you will be traveling through, and there will be an attenuation that happens for this amount. If the source was created, say at redshift 0, then at 11 billion years after, you have this sort of attenuation. And then if it was created, say 4 billion years after the between the Big Bang and 4 billion years, you'd have an attenuation which looks like that. This is the nomenclature here is a little confusing. I stole the plot. An easier way to see this is the following. So these are gamma ray sources, and these are the highest energy photons that we can see from them. And they're color coded by what we expect their tau to be, right? So the absorption tau gamma gamma. And so what you can see is that this is the theoretical sort of limit here. And as a function of redshift, the universe is opaque to gamma rays that are being produced here. Right? You generally see that you're not getting very many photons above this curve, which is the curve given by tau here, predicted by tau. And so this is obviously kind of bad if you want to study high energy sources at high redshift. But what's kind of interesting is that if you see a photon up here, you know that the source actually has to be relatively close, because it would be attenuated and lost via pair production processes if it was further away. And so you actually have a redshift measurement from gamma rays, which is pretty amazing. Right? So if you look at the spectrum of gamma rays, if you see energies up to this range, you know that they're very close. Okay, I'm kind of running out of time. There was one other thing I wanted to talk about, which was the saturated pair production. And so if we have a source which is super compact, so the compactness parameter is greater than 1, the photon density should be very, very large, right? Because this is just luminosity divided by the radius. And so the cooling time scale for inverse Compton is going to be relatively short. Typically, this will be shorter than the crossing time of light across this region. And so this thing, it depends not only on the gamma rays, but also on the electron production process. And it depends on, effectively this compactness parameter. We can rescale this, right? The luminosity is related to the cooling time, and the compactness also has this factor R. So the compactness is related to this. And we know that leptons can cool in a very, very short time. They could cool via radiation or via inverse Compton. And so one issue is then, if we want to maintain the energies of the electrons, we have to replenish the dead leptons, which are going to cool relatively rapidly via other processes. And so there's two ways of doing this. And one is heating by some mechanism. And so here we have a competition between energy loss via various mechanisms and energy gain. And so we can consider the cooling rates are inverse Compton. Inverse Compton is going to go as gamma squared. And so typically it's going to win at very high energies because this is going to go up rapidly. Heating ends up winning at low energies. And so typically here, we can talk about like a specific energy where we would achieve balance. And typically one of the things that is sort of interesting is that in most physical cases, inverse Compton is the way things cool as opposed to pair production. So typically inverse Compton will win out before we start producing pairs, or we start, we will run out of dead leptons. We will have dead leptons, so we cannot then reproduce photons or go through a sort of catastrophic loop process. Now, we can imagine a situation where we have all the leptons are quickly shifting in energy towards some energy where balance happens. So we have some initial spectrum of electrons. The hot electrons are going to lose energy to the point where the heating and cooling balance each other out. Now, the way you would heat them either it could be through magnetic processes, right, where you're accelerating them, as we talked about at the start of class, or via interactions, Coulomb interactions with protons. And so then you would accelerate them again. But they will generally form this sort of monoenergetic distribution right around this energy balance. This will broaden a little bit through diffusion. And so, we may end up forming a Maxwell particle distribution, even if the particles are not directly exchanging energy between them. And the other way to replenish this is to inject new energetic particles into this process. And one way of injecting the particles is via a shock. And so again, this is the sort of magnetic acceleration. So you have a shock that's moving through, compressing, you have a compressed magnetic field, and that's allowing you to accelerate these particles. And generally the particles are accelerated on a time shorter than the cooling time, right? Because if they were allowed to cool, they would never be able to accelerate that up to that energy. And so you can think about particles, they generally have to be accelerated over a very relatively small region of space. And so you have something which is accelerated, and then as they move out, they might start to cool. The other example here is, you could have proton-proton collisions, or another example where you would be able to exchange energy. And so we could think about this process where we have some stratification as things are moving downstream and losing energy. We might have some, most of the energetic particles are going to be close to the shock front. And my alarm is going off. I need to stop. So then we also might have some proton-proton and photon-photon interactions, which feed this a little bit further on, but we're going to neglect those for the moment. So we have an injection and a cooling mechanism. We're going to say they're homogeneous. And so we can think about an injection of electrons per second, and that would be given by Q. This is the injection rate. And so we can then think about a density of photons. So this is the number of leptons as a function of their energy. We can think about the number of leptons in terms of a density. And so this is going to give us some total density. And what we want to have is an equation linking those two. So this is the injection rate, this is the total density, and this is the change as a function of time. And so this is just going to be, taking the derivative of this number density, how many it's being lost here, and the injection. And so this thing is going to evolve in time. And if we want a steady state, this has to be equal to 0. And we can then solve this under that criteria. So we can move these on either side and just take this, this sort of integral of this thing over various electron energies times divided by this derivative, or the loss in energy. And so if we assume that the injection rate goes as some power law, and we assume that the cooling rate goes as gamma squared, then all the particles are generally going to cool down to this factor, and then we're going to assume they disappear. And so we can think about two cases. And one is if S is less than 1, then the number density is going to eventually come to this sort of ratio. If S is greater than 1, then N is going to come to this ratio. And so we again have this sort of division here, depending on what this injection power law is. And if we initially have a monoenergetic injection rate, then we would have this. If this is a power law, then we end up having a spectrum which comes out. And this spectrum will always have an alpha which is related to this. Right, so if we have S here, we can relate it back to this P. And so if we think about this in terms of, we have a process of how the spectrum will sort of interact with and affect the pairs. If we think about a closed region, say an accretion disk, if we continuously inject electrons throughout the region, then we also, and we think about this as, okay, we have a monoenergetic injection ring. And then we assume that the inverse process is, the IC process dominates here. We can think about what's going to happen with this, how it's going to evolve in time. So we inject this, right? So we whoops. Yeah. So we inject this with some monoenergetic rate. It's going to cool at this rate. And what's going to happen? So after the cooling, the number density is going to look like this. And the inverse Compton spectrum is going to have a luminosity, which ends up looking like this. Right. So this is just, oops. And we're going to have a maximum photon energy here. And this is going to be above the pair production threshold. We're going to have a very compact region. And so we're going to have the process sort of begin to generate sort of second and third sort of cases here. And so what happens is all the high energy photons will be absorbed and produce more pairs. This is known as a saturated pair cascade. We generate pairs, and that means that besides the injection rate, we just have a new injection term, which is from these photons which were generated. And so we call this injection term P, and so we have a slope for P, and so we plug that back in, and so the injection rate P is proportional to the change in the number density of photons times 2 gamma. This is proportional to the luminosity, and then this thing is then going to be proportional to this thing, or to gamma to the -1/2. Given that we had basically gamma, or sorry, this alpha here is going to be changing and changing and changing each time we go through one of these pair production and annihilation processes. So we have a new term and we plug it in. And so we have a new spectrum of electrons here, which have this energy. And then we sort of go through this process again and again. And the sort of the point of this is that after a few generations, you take an initial spectrum which looked like that, and you have an initial sort of production of new photons via the electrons. And so you create a photon field that looks like this, that interacts with these photons, produces pairs. The next set of pairs produces this, that interacts with this. The next set of pairs produces this. And then after a while, you get a spectrum which looks like this. So after you have many, many sort of saturated pair productions, you end up with a spectrum which ends up looking like this. So you don't really have a lot of photons that are able to go through this process anymore, which is sort of interesting. So each time you do this, you kind of diminish the alpha, right? So initially you had alpha here, and you kind of asymptote to something which looks like this, which is given by this equation. Okay, so that's all I really wanted to say. The final thing was just that there is one astrophysical place where this may be important, and that's in massive stars. And so generally speaking, you have a massive star where you're not able to produce any more photons to sort of build it up. And so you have a huge pressure, and that drives the temperature up. And so you have a very hot black body, you may be able to generate gamma ray energies here. And as you're compressing this thing down, you generate more gamma ray energies. And then these gamma rays will produce pairs. And the gravity is still pushing these down. The pairs don't have anywhere to go. And so they also keep increasing in energy. So then they'll produce gamma rays, and then the gamma rays will produce pairs, and so forth, until you end up with something that has enough pressure to blow the star apart. And this is known as a pair instability supernova. And so this is thought to be a possible mechanism by which stars in the range 130 to 250 solar masses, and with relatively low metallicities, so they don't have any other outlet to get rid of the energy, that they might explode. And there's been a few supernova where people have claimed that this might be the energy production mechanism that does it. Okay, sorry, I went along here, but I wanted to kind of cover all of this in some detail. So coming back to Roy's question about Hawking radiation, what happens at the near the surface of a black hole is that the temperature becomes very, very large, and that temperature, generally speaking, you can think of that in terms of, let's find it here. You know, so you have some photons which are near that surface, or you have some particles which will end up getting created, and one of them will end up sinking into the black hole, and one of them will move out due to the momentum conservation. And in that process, what ends up happening is that you end up depleting the mass of the black hole by that process of so-called Hawking radiation. Now, it's not clear that it's actually been seen, but it is a process that in theory might work. I don't know if that doesn't adequately explain it. I can try and explain it a little bit better with pictures at the start of next class for you, Roy. But that's essentially what's happening here, is that it's related to pair production. Okay. Anything else? Questions? Okay. I'll talk to you guys later. Some of you owe me a homework assignment tomorrow. I'm going to send out a new homework assignment tomorrow as well. Okay. Okay. All right. Take care, everyone.
Bye.
Bye bye.
Bye.
Bye. Thank